Today's lesson is short and I think easy to understand. It is on the strong nuclear force and binding energy. The strong nuclear force is one of the four forces of nature. The four forces are gravity force. We studied both Newton's version and Einstein's version. Electromagnetic force. We studied this also. But you should realize that it is also responsible for our everyday interactions. The weak nuclear force, that's our next lesson, and the strong nuclear force, which is the strongest of the four forces, but also acts over the smallest distance, the distance of an atomic nucleus. The strong nuclear force is responsible for holding neutrons and protons together in the nucleus. The strong nuclear force also holds the energy that is released in nuclear weapons and nuclear power plants. The mass of the nucleus is less than the sum of its parts. Did you get that? As bizarre as it sounds, the mass of the nucleus is less than the sum of its parts. Let that sink in. The mass of the nucleus is less than the sum of its parts. Here's an example. This is a nucleus of a helium atom. 2 protons, 2 neutrons. Starting on the left, each proton has a mass of 1.0073 atomic mass units. Each neutron has a mass of 1.0087 atomic mass units. Add these up and you get 4.0320 atomic mass units. But if you actually take the mass of the helium nuclei, it is 4.0015 atomic mass units. The whole is less than the sum of its parts by 0.0305 atomic mass units. This difference is called the mass defect. What is this mass defect? It's the energy holding the nucleus together, the binding energy. Using Einstein's equivalence of mass and energy formula, E equals mc squared, we can convert the mass defect into the binding energy. First, we would have to convert atomic mass units to kilograms. 1 atomic mass unit is equal to 1.665 times 10 to the minus 27 kilograms. Then we would have to multiply it by the speed of light squared, which is 8.9874 times 10 to the 16 meters squared per second squared. This gives us an answer in joules, but nuclear physicists prefer to work in mega electron volts. So we convert joules to mega electron volts. 1 mega electron volt is equal to 1.60217 times 10 to the minus 13 joules. But since these three numbers never change, the conversions of atomic mass units to kilograms, the speed of light squared, or the conversion of joules to mega electron volts, we can combine them all in one number and one conversion. 931.494 mega electron volts to atomic mass units. Does everything for us in one step. Let's do some examples, then you can try some.
Let's try and find the binding energy for a particular isotope of aluminum. Aluminum 27 to be specific. And remember isotope notation. 13 is the atomic number of protons. 27 is the number of protons plus neutrons. We happen to know that the nucleus of this isotope has a mass of 26.98 0.1534 atomic mass units. So we need, first of all, to find the mass of all the protons. And there are 13 of those, times the mass of one proton is 1.007276 atomic mass units, and when we multiply that out, we get 13.0945 atomic mass units. And we also need the mass of the neutrons. And remember, it's 27 less the number of protons, so that would be 14. There's 14 neutrons in this isotope. It's 1.0, the mass of one neutron, 1.008665 atomic mass units. When we multiply that out, we get 14.12131 atomic mass units. And when we add these together, we get 27.215898 atomic mass units. So notice, the mass of the nucleus is less than the sum of all the parts of the nucleus. And this is referred to as the mass defect. And the difference then is 27.2158898 atomic mass units less 26.981534 atomic mass units. And when we do that subtraction, we get 0.234364 atomic mass units. And what is the mass defect represent? The mass defect is the binding energy that's holding the whole nucleus together. So this is equivalent to the binding energy. But we want to express it in units of megaelectron volts. So normally to do that, we'd first have to convert the atomic mass units to kilograms. Then we'd have to multiply by the speed of light squared. And then we'd have an answer in joules. But nuclear physicists prefer to use megaelectron volts, so then we'd have to convert to megaelectron volts. But since those numbers never change, we can combine them all into one conversion number. So we take our mass defect, 0.234364 atomic mass units, and we're going to multiply it by the conversion factor of 931.494 megaelectron volts to every atomic mass unit. So notice atomic mass units will cancel, and we're going to get an answer in megaelectron volts. And when we do that multiplication, we get 218.30866 megaelectron volts. And that is the binding energy that's holding this isotope together. And we will find out next time how we actually release that energy and use it. Let's try another problem. But this is how you should organize your work. And it's not very difficult at all if you do that. Let's try the isotope of potassium-39. Potassium-39 nucleus has a mass of 38.963707 atomic mass units. The mass of the protons, there's 19 protons times the mass of one proton, which is 1.007276 atomic mass units, is equal to 19.138245 9.44 atomic mass units. The mass of the neutrons there are how many neutrons? Oh, this one's easy. Subtraction is 20 times the mass of one neutron is 1.008665 atomic mass units. And when we multiply that out, it's 20.173300 atomic mass units. And then we add those together, 39.31154 atomic mass units. And notice once again, the mass of the constituent parts of the nucleus is greater than the mass of the nucleus. And the difference between those is the mass defect. And so that's going to be 39.31154 atomic mass units minus 38.963707 atomic mass units. And when we do that subtraction, we get 0.347837 atomic mass units. And again, that mass defect is the binding energy that's holding the nucleus together. And now we just want to convert it to megaelectron volts. So 0.347837 atomic mass units times the conversion factor of 931.494 megaelectron volts per one atomic mass unit. So those will cancel, and we get an answer of 324.006684 megaelectron volts. Okay? Again, keep your work organized, and this is very simple. Let's try another. Neon 21. It's an isotope of neon. The nucleus has a mass of 20.993847 atomic mass units. The mass of protons is going to be, well, there's 10 protons. 10 times 1, proton is 1.007276 atomic mass units, and that comes to 10.072760 atomic mass units. And the mass of the neutrons, again, we have to subtract, but it's easy. 21 minus 10 is 11. There's 11 neutrons. The mass of one neutron is 1.008665 atomic mass units, and that's going to be 11.095315 atomic mass units. And when we add those together, we get 21.168075 atomic mass units. So this is the mass of the constituent parts of the nucleus. That's the mass of the nucleus, and their difference. The difference is referred to as the mass defect. And that's going to be just the difference between them, 21.168075 atomic mass units minus 20.993847 atomic mass units. And when we do that subtraction, we get 0.174228 atomic mass units. And again, this mass defect represents the binding energy that's holding everything together. Remember, it's the strong nuclear force that's holding everything together. But then that produces this binding energy. So we take our mass defect. All we're going to do is convert it to megaelectron volts with a conversion factor of 931.494 megaelectron volts to every atomic mass unit. Atomic cancel. We're going to get an answer in megaelectron volts, and we get 162.211640. Okay. Okay, and now you guys need to try this.